All right, subscribers, welcome back to another episode of Science with Surback. Today what we're going to look into is sections 5.3 and 5.4 in AP Chemistry. Now before we get going, I want to outline a couple of objectives you should be able to meet by the end of this video. So objective number 1, define enthalpy and relate the enthalpy change in a process occurring at constant pressure to the heat added to or lost by the system during the process. Objective number 2, be able to sketch an energy diagram in the given notes when you are given the enthalpy changes in the process involved and associate the sign of delta H with whether the process is exo or endothermic. And objective number 3, calculate the quantity of heat involved in a reaction at constant pressure given the quantity of reactants and the enthalpy change for the reaction on a mole basis. So we get underway here with enthalpy. And enthalpy is defined as the internal energy plus the product of the pressure and volume of the system. And so what it's going to do here is it's going to tie together this internal energy, which we talked about last section, and something we commonly see here, the pressure and volume of the system, which can be helpful in determining if something is gaining heat or losing heat. And so again, just as a reminder, make sure in your notes you are filling out the fill in the blanks here. Those are correlated with those highlighted portions of these notes. So again, just introducing here what enthalpy is, and now we'll move on here. What is this pressure volume work? Because that's something we haven't seen, and I just want you to become familiar with it before we move on here. So pressure volume work is defined as the work involved in the expansion or compression of a gas. Now, we can more easily interpret this here with work. So work is equal to negative P plus the change in volume. Now, here it says our pressure is always positive and it's always going to be one number. The change in volume, anytime you have a change in volume, you're going to have a final volume minus an initial volume. So that's something to keep in mind as we go through this process here. Now, because you could have a greater volume or a lesser volume at the end, our sign of W can change. So if it's positive, the work done on the system work is done on the system by the surroundings. But if it's negative, the work is done on the surroundings by the systems. So remember, signs play an important role here in thermochemistry. And even though I went over this fairly quickly, this is something to review and to keep in the back of your mind as we go through this process. Now, let's tie everything that we've done so far with internal energy and now this new term known as enthalpy. Okay, so with enthalpy, it's not like temperature where we can stick a thermometer in and instantly get the temperature of some system. It can't be measured directly. So we have to measure through this change of enthalpy. And again, you're going to see change of a lot of things throughout thermochemistry, and enthalpy is one of them. So we can't, again, get this directly. We have to go about it in terms of change. Now, this pressure volume work here is another thing that's kind of difficult to understand, but we can do a few things to help us out and correlate what we have here. So I'm going to start out and I'm just going to write down the enthalpy equation. So delta H equals delta E plus pressure times volume. Now let's remember this. That delta E is equal to Q plus W. We learned that from last section. And so what I'm going to do here, instead of writing this again with delta E, I'm going to write down Q plus W. So we have Q plus W. And we just got done talking about this, and I should make this P delta V. We just got done talking about how we could correlate work to this negative P delta V, okay? And so if we rearrange this, let's do this. Let's throw the negative on our other side here. And so let's say we have negative W equal positive pressure times a change in volume. Let's substitute this negative W in for P times delta V. So what we're going to do here is we're just going to substitute plus a negative W. Okay? Well, now we got a unique situation here, and that is this. Our delta H is equal to Q. Now, we're going to add one additional thing. We're going to call this QP to say that this is our heat change under constant pressure. So again, QP equals heat change at constant pressure. And now we can say this. We can go on and we can say this very important statement here. The change in enthalpy equals the heat gained or lost at a constant pressure. All right, so that statement can be summed up by delta H equals Q at constant pressure. Now, like always here with our terms in thermochemistry, it's really important to associate the sign with what we have here. So a positive delta H, I know I didn't have you write this down, but this means that the system gained heat. It got hotter. And a negative delta H means the system released heat or it got cooler. And these can also be correlated with endo and exothermic processes. So a positive delta H means endothermic process or heat went in. An exothermic process means that heat was lost. So let's take this and let's go into some examples going through our process here. Okay, so some simple examples here. We want to know what is the sign of delta H in these particular steps when they're carried out under standard atmospheric pressure, meaning the pressure is constant. And so what that means for us, I'm just going to outline this, is that delta H equals our heat gained or lost if we're at constant pressure. That's a key takeaway here. So in ice cube melting, again, an ice cube melting is going from a solid to a liquid state. It is getting hotter. And because it's getting hotter, that means our delta H is positive, okay? And again, if we want an explanation of this, heat was transferred to the ice cube, which is our system in this case. Now, if we have on this process here, if we have 1 gram of butane combusted in sufficient oxygen to give CO2 and H2O as the products. Again, combust. Think of all that heat you feel when there is a combustion or there is heat released. Key takeaway here, heat released. So because we have heat release, our delta H is negative, and we can have this. Heat is released from our system, which in this case is butane. Now, we're not quite done here because I want to correlate the plus and minus signs of delta H to exo and endothermic. A positive delta H here means that we have heat flow into or an endothermic process. A negative delta H means that we had heat flow out of or an exothermic process. So again, those terms we need to start becoming familiar with how endo and exothermic can be related to our heat gain or loss. And obviously, we can correlate now our heat gained or lost to delta H or enthalpy. Okay, so let's keep going here into our enthalpy change and talk about our enthalpy of reaction and specifically the heat of reaction. All right, so the Hedo reaction is going to be defined as the enthalpy change that accompanies a chemical reaction. So it's virtually the same process we've seen so far, but we know the delta H of our products and the reactants. And so what we do is, again, we see this products minus reactants. That's another key thing that we need to find here, or we need to identify. We've said before, final minus initial is going to get you a long ways in thermochemistry, but products minus reactants is another key thing to keep in mind as you go through this process or doing some problems with thermochemistry. Now, a lot of times you'll see delta H of the reaction written as delta H RXN. So that's just some information that you should know as well. Now, we have an example here of the heat of reaction, and we can also classify this as a thermochemical equation. So I'm going to draw an arrow because this is a thermochemical equation, and it's just defined as a balanced chemical equation that shows the associated enthalpy change. So it's a chemical equation that shows the enthalpy change. I'll draw another arrow here, and that's just saying delta H here. Now, delta H is dependent on the number of moles of reactants and products in the balanced chemical equation. And we'll get to that here in a minute when we go over the guidelines for thermochemical equations. Now, what we can also do is we can draw these enthalpy diagrams to represent what we have here. And I'm going to talk about this in a second, but I want to go a little bit more into detail here of our enthalpy of reaction examples. So what this is saying here, this whole equation that's written out, is this. When 2 moles of hydrogen are burned to produce 2 moles of H2O under constant pressure, there is a release of 483.6 kilojoules of, again, heat. All right, so remember, we can associate endo and exothermic processes to what we have for delta H. So if we release this much energy, this means that delta H is negative, and so a negative delta H is going to correspond to an exothermic process. Now, we can also talk about here our enthalpy diagrams, which I know it's kind of small here, but with our enthalpy diagrams, what we're going to have is a couple of different things. Obviously, you can see the reactants and products that are involved in this particular equation. And so we have another thing that we can talk about. It says delta H is less than 0, and the arrow is pointing down. If that process is true, then we have an exothermic process. Now, just a side note here, if it's an endothermic process, the delta H is greater than 0, so delta H is greater than 0, and the arrow is going to point up towards the products. Okay, so again, key parts of our enthalpy diagrams is we're going to have the enthalpy. If it goes up, that's a positive enthalpy. If it goes down, it's a negative enthalpy. And you're going to have your reactants and products listed somewhere on that chart. Okay, so now I just talked about some guidelines here about delta H being dependent on the number of moles. And so what we can do now is we can specifically go over what that means. So the first property here of a thermochemical equation is that it is an extensive process. And so what that means is it's going to depend on how much you have. And so if we do this, if we take the same equation and let's say we have double the amount of what we have listed here, I'm going to put this in parentheses and I'm going to say times 2. So instead of 1 CH4, we're going to have 2 CH4 as a gas plus not 2 oxygens but 2 times 2, so 4 oxygens as a gas, is going to yield 2 CO2s as a gas, and 4 H2Os as a liquid. Now when we do that, our delta H, because we doubled everything here, our delta H is also going to double, and so we're going to have negative 890 times 2, and that's going to give us negative 1780 kilojoules. So whatever you do, if you divide, multiply, you have to express that. You have to express that in your delta H. So it depends on how much we have, and that's where we get that extensive property. Now, the next thing here is it says the sign of delta H depends on the direction of the reaction. Okay? So if you reverse the reaction, you reverse the sign of delta H. Okay, so let's do this here. Let's flip-flop our products and our reactants. So I'm just going to draw some arrows here. So we're going to start with CO2 as a gas plus H2O as a liquid is now going to yield CH4 as a gas and 2O2 as a gas. Now we flip-flopped our products and reactants. That means we need to flip-flop our sign. So no longer is it negative 890, but our delta H here is a positive 890 kilojoules. Flip-flop your products, reactants, you flip-flop your sign. The next thing here, it says enthalpy change depends on state of the products and reactants. So I'm going to say this. I'm going to say states of matter matter. And let's change some things around. Instead of using liquid, let's change this H2O to a gas. And so what that does is it's going to change our delta H value. So if we have CH4 as a gas plus 2O2 as a gas, it's going to yield CO2 as a gas. And instead of liquid water, let's say we have gaseous water, so 2H2O as a gas. Our delta H is now, because we've changed from a liquid to a gas, it's going to be negative 8O2. So states of matter matter, and it's especially going to play a role as we get into some problems involving Hess's law, but we'll get to that point. So those are our three rules. If we multiply or if we divide, it's going to change our H by what we multiply and divide. If we reverse our reaction, it's going to flip our sign. And then if we have a different state of matter, solid, liquid, or gas, it's going to also change our sign. So we'll end here with another example, tie in a little bit of stoichiometry to this business with thermochemistry. Okay, so what we do here, it says how much heat is released when 4.50 grams of methane gas is burned in a constant pressure system. Well, we have the thermochemical equation, and what we need to do first is we need to convert this 4.5 grams of methane, which in case you didn't know, methane is CH4, and we need to convert it into moles. So we start out here 4.50 grams of methane, CH4, and we set up our conversion factor. So again, diagonal units cancel out, so we're left with grams of CH4, and we're going to go to moles of CH4, okay? And so what happens here is this. Number one, the molar mass of CH4 is 16.04 grams per mole. And again, the 16 number is associated with grams, so it goes on here on bottom, and that is per 1 mole. Now, here's a very key thing, and I'm just going to set up the units right now, and that's this. Diagonal units cancel out. Moles of CH4 to kilojoules, okay? So we'll get to that in a second here, but we kind of revert to what we talked about already in notes. The number of moles comes from our coefficient. So I'm just going to draw a big line here, and I am going to put a 1 coefficient, and I'm going to put this note here. The number of moles of CH4 comes from the coefficient. And then the number for kilojoules is right here as listed, negative 890, okay? So what we do here to calculate all of this, what this ends up equaling is this. We take 4.50 divided by 16.04, we press enter, and then we multiply it by negative 890, and we get a value here when we round it to 3 significant digits of negative 250 kilojoules. So again, the key takeaway for all of this is you need to get it into moles, and this mole down here in this bottom right-hand corner becomes your coefficient. So if we would have had a 2 or a 3, we would have put that respectively. And so that is how much heat is released when we have 4.5 grams of methane. All right, so this concludes this episode of Science with Surback. As always, I hope you have enjoyed, and if you haven't done so already, make sure you subscribe.